far as I understood. The point is, as usual, like we must lecture on how to learn. I'm trying to learn this myself, so let's try to understand this together. So the first question as an introduction I want to ask is, what is this? So the idea is that in 2 dimensions, so in 1 plus 1 dimensions, the theory of fermions. Can everybody hear me?
Yeah, but it is a little bit something.
The theory of fermions can be written completely in terms of a theory of bosons. That's the idea of bosonization. But this immediately brings us to the next question. How on earth is this possible? Because we have learned in our past life that fermions are a different type of objects compared to bosons. Fermions have half integer spins. Spin is 2. Spin of bosons is integers. How can we write fermions in terms of bosons? Another thing that we know of is if you swap fermions, you get a sign, while swapping bosons. So let me give some arguments on how it can be even possible, 1 plus 1. After all, what's special about bosonization is 1 plus 1. So the idea is, in 1 space dimensions, rotations do not have any meaning. Right? If you just have 1 space, you cannot rotate. Rotations. As a corollary, spin also doesn't mean much in 1 spatial dimensions. So we can hope that some sort of equivalence is possible. But what about the statistics? How do I understand swapping giving rise to negative sign, or even for the fermion case, I have a fermion and an antifermion, which when I bring together annihilates into vacuum. But for a boson, it's a real boson. How do I understand that? So we will see that the bosonic theory that we will discuss will have solutions like this. In space, it looks like this. These are called solitons or kinks. And it turns out that this kink will represent a fermion. Likewise, we will have an anti-kink as well. Which, as you guessed, will represent an antifermion. And you can imagine that bringing them together will make it into a vacuum, just like fermion and antifermion. And we will see in detail, so though I don't have a Peter Arnold style explanation for this, that whatever operator that creates this kink, if you swap them, you get a minus sign. I know this only in details. I do not have a physical intuitive explanation for it. Right. So next we can also ask the question, why do we first answer is, well, this is a 1 plus 1 dimensional QFT. Our world is 4 dimensional. So why do we care at all? Well, this is interesting, that's the first reason. The second reason is, Gary will find it useful. It's useful in condensed matter physics. And originally it was started, the program was started by Julian Schwinger. He studied 2-dimensional QED as a consolation because he and others were not able to solve 4-dimensional strongly coupled quantum field theories exactly. But Schwinger managed to solve QED2. Exactly. And QED2, as it turns out, shows properties such as confinement and mass gap. We will see this through the eyes of bosonization later. So these two problems, if you don't know, are these two conditions. We know that it exists for QCD in 4 dimensions, but we are still not able to solve it analytically. If you are able to solve it, it's a millennium price problem. You win $1 million. All right, I think that's enough information. Now, let me just lay out a plan. So today we will talk about fermions. 2D. If I get time, I will also talk about something called the chiral anomaly of massless fermions. Only schematically in Peter Arnold way. In fact, I learned it from Peter Arnold. So the next lecture, we will talk about T-duality. And this is a condition for the kind of bosons that we will study in 2 dimensions. This lecture is also a skippable lecture in the sense that I can do away with it. I can do it in 10 minutes. Or I can just stretch it out into one full lecture because there is a lot of interesting geometry involved. So I will leave that to audience consideration. And then in the third talk we will talk about bosonization, the actual map between fermions and bosons, and the last fourth, or maybe to go to fifth, we'll talk about QED2, these are examples of bosonization. Right? So let's start with fermions. I think we can go through this pretty fast because it's going to be pretty trivial for most of us. Conventions, we have the metric to be that it's, I don't know, it's not mostly plus or mostly minus, it's equal amounts of things. And the Clifford algebra is that, and we can choose gamma 0 to be fermion that we will study obviously has the action dx. And psi is the two component. Any questions so far? If you have questions, of course. Yeah. So, yeah, can I do that? What that means is that I have two components, two complex components for psi, and I can, as usual, use gamma phi to decompose it into psi plus and psi minus and so on. Now we also define bar as radical gamma 0, which is it flips the order because of gamma 0. These are all just definitions. So if we write the action in terms of this while basis, what we get is
Just a notation question. In the action, is it I partial slash minus
Yeah,
M?
yeah.
What does this partial slash mean?
slash is d mu gamma mu, that would be 0 gamma 0 plus d gamma 0 plus gamma 1. So this will be a matrix. We can figure it out. So this will be 0 d minus dx. Yeah, we are not going to use this, but that's how, you take this matrix, plug it in here, put these things as matrices here, multiply everything out, then you get that. Yes, Ken?
No, it's
Yeah. So, seeing this, it's natural to define light coordinates. So we define x plus minus x, and e plus minus e plus minus x. So this is nothing but minus e plus. Just definitions. All right, so let's take a special case of m equal to 0. Why? Because we immediately see that plus and minus don't talk to each other if m is 0. The only coupling between plus and minus comes from the mass. So if we have m equal to 0 and we find equations of motion, what we see is that the minus on psi plus is 0, which means that psi plus is a function of e plus x only. 0 case, you have two solutions, psi plus and psi minus. They are independent in the sense that psi plus is a wave that moves to the left, psi minus is a wave that moves to the right. Is that clear? So this is we will call it right member. This is sit up. This is left member. This is just as a matter of remark, people often take e to I tau in the Vic-rotated case. Then they would call psi plus the holomorphic solution and psi minus the anti-holomorphic solution. Just as you, the Z and Z block. Not important. So the point is mass equal to 0 fermions are chiral, which means that you have a left moving component to the solution and a right moving component solution, which separates out into each other, independent of each other. Any questions so far? Now we can talk about symmetries. Okay. What are the symmetries of this action? The first symmetry is you can take psi and multiply by the face, or in full matrix notation, this is a symmetry even if you have a mass, right? This is the standard global phase symmetry that we have seen in complex field theories, and we can do and find the corresponding current, which we know is there any confusion with this?
Is that a V in the subscript?
Right, so the V stands for vector, because, so this is why do people call it a vector symmetry? I don't know the history of the name, let's just call it a vector. We will have an axial vector symmetry now. The second symmetry is only applicable in the m equal to 0 case. So in the m equal to 0 case, remember over there that psi plus and psi minus do not mix with each other. So I can do this, for example. Sorry, I messed it up. In the first case, it's the same because it's just that. Now I'm doing this with the psi plus and psi minus rotating in the opposite way. This, in a compact way, can be written gamma phi member is this, and you see, e to the this matrix times theta is nothing but that. And this is called the, we do not for that, the final current, we will call it the axial or chiral current. And we can find it, the only difference is this gamma phi. Find it in that. Any confusion so far? This will go very fast. Right. But keep in mind that this only is a symmetry when mass is zero. If mass is not zero, psi plus and psi minus mix, and I cannot rotate them independently. Okay, now let's try to quantize. So if you feel that this is a bit too fast, that's because there's nothing much to say. This is the same story that Peter Arnold might have thought. So let's do quantization for psi minus, which is a function of x minus only, and remember what x minus is over there. For psi minus, so these are waves that moves to the right, and their dispersion relation for the minus guys is just that. It's greater than 0. Is that obvious?
Why is P greater than 0?
Because it's moving right over.
It's still a negative, if you have negative P and negative energy, right?
Yep,
So-
that's also possible. So this energy is, by this I mean the actual energy of the excitation. So, that's the dispersion for all values of P. And you can find it by writing the mode expansion. Which is B minus x plus C minus and using the equations of motion or something, but I'm just going to, bypass all that because it's the classic thing that we've done. So since P I'm confused about something now. We can just do it. If you plug this in here, P dot x is nothing but P0 P minus Px. P0 is nothing but EP, which is P. So I get P minus x. So I have P to the I P x minus plus C. we have that. And we can do similar stuff for psi plus and find, in this case, for psi plus the dispersion in substitute value of p, and because this is left move, and psi plus c minus infinity to 0 pi plus p pi x squared plus c delta plus any confusion so far? Just did the same thing, but with this dispersion. I'm waiting for questions if there are any. We can find canonical conjugate momentum. That, which is nothing but, the derivative from the right. This is a matter of definition, but that's how it's different, of the Lagrangian, and this is going to be just I psi dag if you do that here, or it's clearer there. Then then we can impose quantization minus pi plus delta x plus y pi x minus y, and these are anti-commutation relations because these are fermions, so on, and then plug this in and find out b minus p pi minus q is 2 pi p minus q c minus p c delta minus q is 2 pi delta minus q minus q. Same for plus, and the plus minus do not commute. C and B do, well, plus minus anti-commute. C and C plus, C and B also anti-commute. There is nothing here, 0. Is that clear? I don't want to do this derivation ever again. So I just state.
There's only one confusing thing, which isn't actually this, it's notation though. The conjugate, the daggers,
Yeah.
are plus, they look kind of like pluses. And we deal with,
Both are the same thing.
we deal with subscript minus and plus, but also the x are plus minus. So
How do I make the notation better?
I don't really know.
I think
The X,
Change fields.
originally you had subscripts on the X plus and minus as well, right?
Did you have subscript?
yes.
So that might make more sense.
No, the subscripts, look at this,
No, it's
top board, x
Yeah.
plus minus, and that makes sense,
You know,
they're supposed to be
These are the
components.
chi,
Oh, I see, right, because
chi
there
of
is sort of,
wild basis or something.
Yeah.
okay, so the X plus minus, you want it
Also
upstairs,
has plus minus.
you want it upstairs because
Yeah,
It's like
contravariant. or
Yeah,
something, right?
covariant contravariant,
Okay.
so, yeah.
So I don't know, there is no way to.
I don't know, just, yeah.
let's do some actual calculation.
I was writing subscripts on X and then it's. I didn't realize that.
Impulse.
Why didn't you use a void as opposed to 100?
Because.
So since we are dealing with a free theory, we can just compute 2-point functions and that tells us everything about the free theory. So we'll attempt to compute psi, say minus y. And we have to keep in mind that we have to put a regulator somehow. So the regularization we're going to do is this. We'll put a cutoff in this manner. For large P, you have a cutoff. Then let's try to compute that. So you have 2 psi and psi dagger, and this, by the way, means vacuum expectation value between vacuum states. Then, which I forgot to do, is we have defined the vacuum to be annihilated by B's and C's. This is how we define the vacuum. That means that from the psi dagger, which will have a B dagger and a C, the C part we can forget, and from the psi we can forget the C dagger part, which it adds to the left. That's clear, right? I'm going to just do it quickly. So psi minus x, psi minus y is going to be, I will have 2 integrals. And then from the psi dagger I will pick B dagger. So I have a B minus dagger Q. And from the psi I will pick up a B. So I will have a B minus Q. So with the B I will have e to the I B x, and with the B dagger I will have e to the minus I Q y, I will have e to the minus p by 2 lambda.
So px minus and y minus. Right?
Yeah, just drop 1 minus.
Y.
Just for
Alright.
ease. That's okay, right? All the other terms vanish.
Yeah.
Right? The other terms being from psi dagger, I'll have a C acting on vacuum vanishes. From psi I would have a C dagger, but C dagger acting on the vacuum to the left vanishes. So this is the only thing I have left. And this we already know how to evaluate, right? So this I can write as P dagger minus Q minus P plus or so plus 1 I will have it B commutative. And this thing, vacuum expectation value is 0 because V acting on the vacuum is 0. And this we already know is equal to 2 pi delta Q minus Q. So that sets P equal to Q. So in the end we will have one integral left because Q integral can be done. And into the I, P, X and sorry, P and Q are the same, so I have P X minus Y e to the minus P by Q. And this integral can be done very easily. We all know how to do the integral. And this is equal to I by Q by X minus Y plus I epsilon by epsilon is 2. So I guess I can skip the next calculation. Let's just say what it is. It's just similar, done in exactly the same way. So even though we computed this, we will just keep it in reserve for now. We will use this in lecture number 3 where we actually derive bosonization as matching the correlators between bosonic theory and the fermionic theory. Okay, and that ends the parts that we need for bosonization, but we need one extra feature of this theory when we discussed QED2, which I think I will introduce now if everybody has patience.
Yeah.
So that's the anomaly. Try to do this in the Peter Arnold way, so we understand what it means, and we'll skip, some detailed calculations. So we are going to focus in the mass equal to 0 case, which we remember that as an additional symmetry, which is called the axial or chiral symmetry. If we compute, the charge corresponding to each of these currents, this will be the total charge of the fermions, and this is the number of charge of the fermions minus the charge of the antifermions. We just have to plug in what psi and psi bar is in terms of these mode expansions and verify what that means. But the idea of chiral anomaly is that when you quantize this theory, this symmetry will be broken in the presence of an electromagnetic field.
Is it the charge of the fermions minus the antifermions, or of the or the right moving fermions?
Oh,
minus
yeah.
the left moving?
That's right. That's right. So, yeah, that's what I meant, but I said it wrong. So this will give us the charge of right movers plus the charge of left movers. This will give us charge of right movers minus the charge of left movers. Just have to plug this in and see, or just believe
told you.
me for now. We are not going to use the experiment existence of electromagnetic field, and when we try to quantize this theory, this symmetry will be broken. So to see this, we will restrict ourselves to space be finite. Zero L or something. Then we will use the Dirac picture of the vacuum, for example. So the Dirac picture, if you don't remember, is what follows. So the dispersion relation, first of all, let's recall that for right movers it's that, and for left movers it's that. So in the first quadrant I have E equal to P both greater than 0. So that's a right moving particle. So right moving particle R and P. Over here I have P equal to E both less than 0. So P is less than 0. So how do I say that this is the right move? But remember, in Dirac picture, negative energy means things are moving backward in time. So negative momentum moving backward in time is actually moving to the right. So this is right moving antiparticle. So now we can guess what these things are. Here we have E equal to minus absolute value of P greater than 0. So this is left moving particle. And here we have E again equal to minus absolute value of P, but now less than 0, which is left moving anti-particle. So you all remember what Dirac picture is? He fills up all the negative energy states. Right? So the Dirac is, you have these states. Why do I have discrete states? Because of the signs. The momentum can only take values. Momentum is 2 pi, something like that. Or is it pi by L?
Depends if you're doing periodic boundary conditions.
So let's do that. Okay, so the momentum takes discrete values,
Periodic.
and you have available states to be all of that. And in the Dirac picture, what you do is, oh man, I drew it too many. You fill all the negative energy states. And that's the vacuum. Now the idea is, we have two symmetries. We should be able to do some deformations or perturbations to the theory such that the symmetry do not break. Any perturbation that we do at the action level that do not break the symmetries should not violate these two symmetries in this picture. Okay, let's try to do something simple. First we will create a right moving particle-antiparticle pair. What does that mean? So that means I put a hole here this is a right moving particle, and this is a right moving antiparticle. Right? Now, let's see. So, the total charge, how much did it change? It did not change at all, right? You have a particle and antiparticle. They have different signs for the charge. By the way, particle is created by, let's say, B dagger. Antiparticle is created by C dagger. And they would have opposite charges. Again, Peter Arnold QT. So, overall, this did not change. Let's find how much the Q5, which is the chiral charge, which is number of right moving fermions minus the number of left moving fermions. So multiply by their charge. So here, this also do not change, right? Because I created a right moving particle and an antiparticle, their charges just cancel. So initially I had infinite number of right movers with negative charge or something. Then I created 1 minus 1, you know. Is that confusing?
So delta Q5 equals, what is that? Infinity?
Yeah, the infinity, I was just trying to convince you.
Is that the change or
The total.
Yeah, initially you had infinite number of them. Now you just split one. You didn't change anything. That's the point.
Right.
So if I count the filled states in the red line, that's still infinite. If I count the filled state in the green, that's still infinite. So nothing changed. The chiral charge, remember, is the number of this guys minus the number of that guys. Right?
So we're saying that the chiral charge of the vacuum is 0, we have to start with, or?
Yes, chiral charge of the vacuum is 0 to start with, because infinity minus infinity is 0, of course. And even after a particle pair production, you have infinity minus infinity, which is still 0.
The states in the positive energy realm are empty still, right?
Yes, yeah, I
Uh,
only have
when-
one filled state,
Yeah,
but
so,
correspondingly I have an empty state in the C.
okay, and the antiparticles all have negative sign, all have negative
Yeah, right now I did not produce a left mover.
Oh, and my question was actually, I'm trying to understand why delta Q is 0, not delta Q5. Why delta Q is 0?
Right, so
Right.
this has +1 charge,
Okay.
and this has a -1 charge.
But then that's an empty state now.
Yeah, the empty state, you think of it as an antiparticle with negative charge.
Okay.
That's the bit of which.
Maybe that also has negative chiral charge as well.
Yeah. So that's that.
Sorry about that. For the rest of the antiparticle states, do they have positive charge?
For these guys,
Like, no, the red curve.
the red curve with empty,
The filled ones.
the
What
filled
yeah,
ones.
what kind of a charges, what is the sign of the charge that they have?
Yeah, this is all positive charge, right?
All of them are positive?
Yeah.
Okay, yeah, because I confuse antiparticle with like having a negative charge.
That is true.
But
The
then,
antiparticle is the absence
Absence
of
of,
the state in the filled C.
but then he filled it.
So the filled C by definition will say has zero charge.
Zero charge by definition.
Ah,
It has infinite charge if you look at it like that,
okay.
but you define it to be zero. Then you take one away from it,
And then it
then it
has-
becomes negative.
Okay.
So the antiparticle is this entire thing.
Okay.
I have a question. I don't really understand the Q and Q5. What's the difference? What is the difference between them?
Right, Q is the charge corresponding to vector,
Okay.
and Q5 is the
Oh,
charge
okay.
corresponding to. So Q is integral x JV 0 Q5 maybe better.
Association of vacancies and state excitation.
Is that okay? Okay, now let's do something else. Let's go back to vacuum, which has zero charge by definition. And then modify the theory in a different way. So we will introduce a constant electric field. So we introduce a constant electric field. So the action becomes into x psi bar I d slash minus e slash n no n. So a slash again is a times gamma p. And a is the electromagnetic potential for two vector potential, and in this case we are taking A to be a background electromagnetic field, just background electric field, no magnetic, just a constant electric field, and this A is corresponding to that constant electric field. So we apply a constant electric field to the vacuum, right? So yeah, I have to look at this. Particles are all, in some sense, charged. And if I apply an electric field, it will start moving. The amount of momentum a charged particle will gain is nothing but E times E, too many E's. E times E times the time period along which I apply electric field. Let's imagine I apply the electric field for a duration of delta T, then the force due to that electric field is that. So force times delta T gives me how much the momentum of each particle has changed. So each of these filled states, roughly speaking, gets a positive momentum, right? So let's imagine that I apply the electric field to a duration of time which takes each particle to its next state, right? The momentum is going to increase by this amount. So if this particle's momentum increased by that amount, this particle's increased by that amount, this particle's increased by that amount, see what's happening. So what will happen is that I will have a filled state there. Likewise, this particle's momentum increased by positive amount. What I will have is an empty state here. So in this case, what is delta QV? So I have one right moving particle and one anti-particle, right? Left moving but still anti-particle. So the total charge is particle plus anti-particle is 0, the change in total charge. So the vector symmetry that we had still is intact. But what is delta Q axial, which is the number of right moving particles minus the number of la la la, is going to be 1, that's that 1, minus 1, which is the chiral charge of an anti-particle, then that's Q. So by applying an electric field, I broke the axial symmetry. And this breakage happened in the quantum picture, roughly speaking, in the rough Dirac picture, Dirac-C picture. The idea is, quantum mechanically, if you have the electromagnetic field coupled to chiral fermions, the chiral symmetry is anomalous. This is the rough explanation of what's going on. So you might ask, what we did is we did something impossible. We produced a right moving particle and a left moving antiparticle. We should be producing a right moving particle and a right moving antiparticle. That's what's allowed to create from the back. But we did the impossible. So we might ask, where did this right moving particle came from? It came from infinity, like Hilbert's hotel. Had we had a cutoff, this is the lowest amount of energy that we can have, then, at the end we will have an empty state. And here, something happens. Then this chiral symmetry will not be broken, because we have compensated. This is compensated by that, this is compensated by that left out thing. But if you put a cutoff like this, what we break is the gauge symmetry of electromagnetism. So, having a cutoff breaks the gauge symmetry. If you don't have a cutoff, axial symmetry is broken. The idea is, quantum mechanically, you cannot have gauge symmetry and axial symmetry together. Right. So, any questions? You'll use this also later.
Yeah, so when you wrote down the action, you promote the first symmetry to, the standard gauge theory, right, gauge symmetry, and you pick up the A slash.
Yeah.
And so I've never seen this before, but you don't touch the chiral symmetry, it's just
a global.
global.
That was gonna be, I think, part of my next question. So what if you try to gauge the
Right.
chiral symmetry instead? So
Right.
you don't put an A, but you put
Right.
Something else.
A tilde, gamma mu, gamma phi or something.
Yeah, that's where this problem really gets, because if you try to gauge this, gauge symmetry is not really a symmetry, it's a redundancy type of thing. And if it's anomalous, that means that, you cannot have a sensible quantum theory with both chiral and vector gauge symmetry.
Can you have one or the other or something?
Yeah, with this artifact.
So, can I not gauge the
Axial
the
symmetry,
axial sym-
yeah.
Can I gauge the axial one, not the regular one, the vector one?
I think it's possible. When you try to derive this anomaly for 3+1 dimension, you get a linear combination of breaking of gauge symmetry and axial symmetry, and then you can tune this linear combination in such a way that you break this one or that. But I've never seen people
might just be a choice of basis or something. Or like if you redefine sine minus or something like that.
With an extra phase or something.
Yeah. Okay, then my other question was I don't see how the association with the cutoff and how it breaks gauge symmetry.
Right.
The energy.
Everybody says this, so so if you put cutoff, why does it break these? I don't know, I think you have to look at the word identity. Yeah.
That's what, yeah, they say that with the momentum cutoff,
Yeah.
you're doing QED stuff,
Yeah.
but I never understood it there, right?
Yeah.
Because dimensional regularization supposedly fixes it, but that's all parallel divergence
Yeah.
to zero, so.
Yeah, yeah. I guess word identity would tell you something, but I'm not really sure. Anything else? So in summary, what we did is we quickly went through two-dimensional fermions, derived some correlators that we will use later, this and that, and discussed chiral anomaly in the Peter-Arnold way, which also will show up in QED2, because QED2 is electromagnetism in 2 dimensions. And when we set mass to 0, we will have this chiral anomaly, and that will correspond to something in the bosonic picture. Any other questions?
So I thought this chiral anomaly stuff appears when the electric field is quantized.
No, you just need to have a background.
Yeah, because in the usual picture is that triangle diagram, right?
Right.
But that's not really like that's like a quantum electromagnetism argument.
Yeah, that's a quantum electromagnetism argument. But you need at least the electrons to be quantized.
Yeah.
But from this picture, it doesn't seem like electromagnetism need to be quantized. You know, here we just apply the background electric field, and that breaks the symmetry. The idea is if you apply a background electric field to the vacuum, pair produces, but not the pair that we naively would think would be produced. It's not the right mover and its antiparticles, right mover and left moving antiparticles somehow. So, yeah, but this is a hand wavy picture too.
Well, even without that picture, that direct C picture, I guess you just calculate the
Yeah.
charges.
Right. But do you need the electromagnetism to be quantized? I'm not really sure. Maybe this is just a hand wavy way of understanding it.
Alright.
I don't know.
Are you done?
Yeah.
Okay.
You have a lot of papers.
Questions for the speaker?
I do have one question, I don't know if I should say it. Wait, so